Hello everyone, thank you for coming. We're Project Titan Hyperion. I'm Harkshan Graywall.
My name is Hugo Drayo. My name is Sherman.
Caesar.
Ian.
And King.
Okay, perfect. So this is our mission statement. So what we're trying to do is we're trying to improve mobility on campus by trying to develop an autonomous shuttle car service. So this is the first car. Eventually we hope we would have more of them and we'll have a fleet of them moving around campus. The way we kind of see it, it's going to be a combination of autonomous navigation and like ride hailing. So combining technologies from such as like Waymo, Uber, and then eventually combining it with like Lyft and Uber, their stuff. Potential applications, we see it at like airports, amusement parks, large corporate campuses, large museums, universities, any sort of large complex where a lot of people need to move around.
And then talk a little bit about inspiration. He talked a little bit about the first 3 companies up there. The reason we kind of wanted to do it, we saw that this campus kind of has an issue with parking, just a small issue though. So we figured, if we can have like an Uber service, kind of just where it takes students from place to place. The goal was trying to get an app going, so that way if someone needed a ride, they could see exactly where it was at, using like a GPS or something like that. And then, yep, that's about it.
We're going over the design goals and requirements. As you see, we split out the 3 parts: control system integration, navigation, and also safety. The goal of the control system is to automate the operation of the golf cart, and like that is by automating the gear shifter, the brakes, accelerator, and steering. And also, we also integrate and mount the sensors and hardware onto the golf cart. For the navigation, we developed the system to automate and navigate the car from point A to point B. Which is so they can determine the destination that they want to get to. Also, we also implement mapping for navigation and safety, and also remote path planning to avoid dynamic obstacles. For the safety, we gather data about navigation, environment, and obstacles, so we determine what obstacles are there so we can avoid them. And also, we transfer data from navigation systems for use for path planning.
So Ian and myself were in charge of the integration of all our components. The first successful component that we integrated is our gear shifter or the transmission. Our cart that we got only has 3 modes. It has drive, neutral, and reverse. You can see in the video that we're going to play that these switches right here are going to move, and that's how we determine what mode we're in. So the first switch closest to the wall, you go back. First switch closest to the wall, that's forward, and the switch farthest from the wall is reverse. And so we use stepper motors and Arduino Mega to control all our systems. And right now, this is just a demo that it's actually working. We're not just saying.
So for the brake and the gas pedal, we had to set up in a way that someone at first could still press on the brake or press on the gas to override the system if anything happened. So the way we did it, which would not be implemented like this in the future, is to have that pulley system in the back, basically pulling on a rope or a cable that pulls the brake pedal and the gas pedal. All that is still run off the same Arduino Mega that gets signals from our main computer, the Jetson. And I've played 2 demos, one of the brake and one of the gas. One thing I should mention, those servos we're using ended up being strong enough to pull, but not fast enough, obviously, for the brake pedal. We need a much faster motor. That's something for future implementation, something that will have enough strength and speed. So that's now the gas pedal and a little bit of the demo of it driving on its own. So obviously that's a very slow motor that's going to need to be faster in the future.
If you notice in the video, he pressed the button first. That's just because we didn't have a Jetson because they were working on it for the computer vision. So we had to simulate the Jetson giving the signal. So we used push buttons to simulate that.
And then I'm going to talk a little bit about basically the steering wheel. We use a motor driver and a motor, 12 to 24 volt. Basically, the motor is going to take low current signal. The motor driver is going to take low current signals, turn them into high current signals. Basically, this is the configuration we had. The motor driver will be here, connected to the motor. We configure a drive chain that would connect the chain to the steering wheel. But the issue that we had was taking the steering wheel off. We actually broke a couple of steering wheel removers in the process. So that is the only issue we had and why we weren't able to actually implement the steering wheel and the motor driver to it.
We were trying to save the steering wheel also because, same for safety, we wanted to make sure that someone could take over if something happened. So we wanted to remove the steering wheel, put the gear, and put the steering wheel back over it. That didn't happen.
I'll touch on the navigation system really quick. This is how we're using the robot operating system. That's going to be the framework that we're using to actually develop the navigation system. It has it's really flexible in terms of writing software, so and it comes with a lot of libraries for navigation and such. So that made some of our development a little bit easier. The hardware, as my team touched on a little bit earlier, we're using the NVIDIA Jetson TX2. It's a $300 embedded board. It's primarily for AI applications, but it's powerful enough for most of the stuff that we were working on. You can see some specifications over there. And then this is kind of an overview of how the navigation system works. All that data, so on this side you can see that there's going to be data coming in from the sensors, from the odometry sources, and then on that side too. And then internally, this is the main system that, in the box right there, that's the main system that's going to be running in the Jetson. So it's going to take the map, it's going to take the goal that we give it, and it's going to try to come up with a plan to actually navigate there. And then there's like cost maps. That's where it's just kind of determining where the obstacles are and what the best path is to the destination. And then once all the path finding is done and the final path is decided, it will actually send that over to the base controller, which is what this is how we would actually interface with the actual cart. So a lot of the software that they developed, that's where that would tie in.
So the way we wanted to actually make the cart safe was using the Z 3D stereo camera and the proximity sensors. The thing about the Z camera is, as two 4 megapixel cameras, it goes for 1080p at 30 frames per second, has a depth range of 0.5 meters to 20 meters, and it has a frequency of 100 hertz. Now the reason we want to use the Z camera is because it works with OpenCV and ROS, like kind of like out of the box. We just had to get some software from them. And then also the proximity sensors. One of the goals we wanted for this cart was to make it low cost to compete with Waymo and Uber and Tesla. So we got low cost proximity sensors, which would cover the blind spots of the Z camera, which was from 2 to 400 centimeters. So the thing with the proximity sensors was we had it to go up to about 2 meters because anything more than that we would get too much latency. And we also get zero readings, which would happen when the proximity sensors would send out a signal, but it would bounce off and it would not get it back.
And then is a demo that we have. It's a live demo. So this is the Z camera, and then you can kind of see it moving around, and that's picking up real-time point cloud data. And the point cloud data is actually sent over to the raw stuff, and that uses that for part of the navigation.
So some of the challenges that we faced were, how do we power our components? The golf cart that we received actually has 48 volts on board. So we used a inverter to convert that 48 volts to a 12 volt output, as well as 120 volt AC output that we use for the Jetson. And it also came with 2 USB 2.0 outputs as well. As Hugo touched on it earlier, we had a lot of problems with our steering, and then our cart was all the steering, the braking, the acceleration, that's fully mechanical. There's no electronic components involved, so we had to basically retrofit motors everywhere, put microcontrollers all over the cart for it to be able to be autonomous. Another issue we had is how do we track our movement? So we're using rotor encoders to track each wheel, GPS to track our location. And another big problem is we had limited access to work on our cart because the first cart we got was damaged so far that we would spend our whole semester trying to fix it. We didn't get this cart until second week into our spring semester, and then we had to move the cart off campus to be able to work on it basically all night.
Right, those are, design alternatives are things that we were thinking of using and we're either able to or not. So we could use, we were thinking about using servo motors for the brakes, accelerators, but those are not, they don't have a strong enough holding torque for the pedals. And we were, before we went with the Z camera, we were thinking about going with two webcams, basically with OpenCV, and to get basically the same thing that we can do with one Z camera, and then it's much more powerful, so we went that way. GPS module was not implemented because it was giving us faulty readings, but that's something with more time that could be implemented. Instead of the proximity sensors, we were thinking about using mini LiDARs and also a main LiDAR on the top, but this turned out to be a much, way too expensive for our project. And something that could be used in the future would be a stronger computer. And yeah.
As you see, this is the overall cost for a project. See, most of our budget went to the Z camera, Jetson, and motor and drivers. The budget that we were allocated for this project was $2,000. As you can see here, we were able to stay under the budget that we were allocated.
Yeah. Sorry. We're good? Okay.
Okay, so we actually met most of our goals. In terms of integration, we actually were able to automate 3 out of 4 systems. The only system we weren't able to automate is the steering. Gear shifter, brake, and acceleration, all complete, working. We also developed a navigation system. That was Harkishan's group.
So, like I said, we tried to make this a kind of a low cost, but also try to compete with the Tesla car and Waymo by Google. We had a budget of $2,000. Although we did get the Jetson for about half the price, we'd probably add another maybe 500 max to actually get the full price of this. And we also overcame technical difficulties. We had limited access to the cart and just had to do trial and error with most of the motors and drivers.
Questions?
I'll give a few minutes for the questions. Can I have the next team?
This is where we blew most of our budget. We had an artist too.
The rights for that photo.
We wanted to commemorate our teammate.
I actually don't have photo cred on there.
Yeah, that photo was taken by Eric over here. We paid him like half of our team's budget for this.
Yes.
So if the camera capturing some image of hindrances, were you able to identify that obstruction and stop the vehicle? Would you consider that kind of thing in your project?
Yeah, so we had 2 systems to actually handle that. So the Z camera would be able to, it does point cloud, so it's just looking at different points. So it would be, if the Z is able to detect it, it will take that into account when it's doing the path planning stuff. So if it already has an obstacle and it can perceive it, it would try to just avoid the obstacle. But in case the Z didn't catch it, that's why we have the proximity sensors all around the cart. And those are more of just a kill switch, so if something is actually blocking it and it gets within the range of the proximity sensor, it will just shut off the cart, and then we'll set a signal back to the Jetson letting them know, hey, there's an obstruction over here, you gotta come up with a different path.
So the eventual goal is to have it like pick you up from a class, take you to another class?
Yeah, so this semester we just focused on just developing the autonomous cart, a lot of that, laying the foundation for it. We're actually hoping our project turns into a legacy project, and then we have people coming in and kind of expanding on it. That's our long-term view, is just kind of having a combination of autonomous cars and like ride hailing. So it could be like something as part of the iFullerton app or whatever. You just let it know, this is where I'm at, this is where I want to go, and then whichever cart is available will come and pick you up and pick it up.
So related to the sensor and processing technology, so you guys covered a broad range, pretty much everything everybody's looking at in the industry, right? Sonar, mono vision, binocular vision, LiDAR, you talked about all that stuff. And so everybody in the industry is, looking at these same issues, right? Trying to understand what the strengths and weaknesses of each of these sensor technologies, and there's religious debates all the way from the top of Tesla and so on.
Yeah.
So you guys have worked, or at least looked at all those different technologies. Did you draw any conclusions from any of that?
So just so some of the things that we kind of looked into was, as you mentioned, there is some debate between the different cars. So famously, like Tesla has just decided to not go with the LiDAR, mostly because LiDARs are really expensive. It was the same decision that we had to make. We explored using LiDARs, but they would just be really expensive. With a camera, we get a lot more data that we can work with, but obviously the camera has some limitations, as you can probably see on here. There are some distortions that we would have to kind of work through. That's kind of the same issue that Tesla ran into, and then Uber's kind of have the same issue. So those were some of the main conclusions that we drew. It's just there's a different, if you have the money and you can spend some money on it, LiDAR would be the way to go. But if we're just trying to be more cost efficient, maybe more of a camera approach with a lot of computer vision algorithms would be the way to go.
Would you say so far the work you're doing is kind of level setting, right? Kind of understanding what's available in the industry, and then sort of more of a system integration project? Is there any area that you think you can add some new ideas and new? So university's always looking for IP development because it's a huge revenue stream and it's great for you guys and your resumes and so forth. Where do you think the new area is? Where do you think you can work?
So definitely with the more focus on the cameras, we could try to come up with better computer vision algorithms. So it's just with limited data, I can just do a lot more with that. This is one of the things we actually, my teammate over here, King, explored, was trying to use a little bit of machine learning to just be a little bit better with the object detection and such. So that would definitely be a way to go. So if we can just build better models, that would help out.
Thank you very much.